And our third speaker this morning is Michael Groom, also from CSIRO, who's going to be presenting on interpretable forecasts of ENSO phase at multi-year lead times using entropic learning.
Okay, cool. All right, thank you very much. So I'm also a postdoc at CSIRO under Terry O'Kane. This work has been kind of performed over the last 2.5 years or so in collaboration with some colleagues in Germany as well. Just briefly like to thank the organisers for inviting me to give this plenary talk as well. It's quite exciting to be able to talk about what I've been doing to this many people. I'm going to quickly kind of put up some links basically that will summarise or hopefully give some kind of context that I won't have time to get into today. On the top right here, this is the kind of first paper where we published kind of initial proof of concept of what I'm going to be talking about, which is applying this entropy optimal sparse probabilistic approximation, or ESPA for short, algorithm, to the problem of classifying, or rather predicting the phase of ENSO, treating as a classification task at up to 24 months lead time. There's not going to be too much kind of specific to climate model outputs in this talk, although I will say that in this paper we applied this to the ACCESS-OM2 surface forced model. But what I'm going to be talking about today is purely done with observational data sets. The bottom QR code here is from a more recent paper where we have applied this to kind of do a rigorous skill assessment of the algorithm when it was applied to just data sets, observational products from the satellite era only, and comparing this against the kind of operational baseline of the IRI ENSO prediction plume, for those that are familiar with it. But what I'm going to be talking about today is really more on the side of interpretability rather than focusing on the skill assessments. Today's going to be really about kind of diving into how the models are actually able to make kind of good predictions of the phase of ENSO at these kind of longer lead times greater than the spring predictability barrier. So I'll give a kind of a few different methods that we have for kind of visualizing this kind of thing. And I'm just going to put this up here now, so in case I don't get time to talk about it later. So a lot of this stuff I've kind of already put out and I'm hosting on a kind of web app that's on my own public domain at the moment. The aim is that eventually this will all be hosted on a kind of official CSIRO web portal at some point in the future. And I'll try and give enough context so that if you do actually go to that website, you can understand a lot of the stuff that's on there. Okay, so a one-slide introduction to ESPA without going into any of the maths. Basically, you can think of this as a clustering method with some additional regularization steps. And so effectively what we have is if you take our data, which I'll explain on the next slide what we're using as the kind of features, the inputs to our model. But basically just you can think about we kind of have our data and we fit a set of clusters to different regimes of the data in its phase space. And we simultaneously learn a set of feature weights that say how important each of the individual inputs to our model is. This is kind of crucial for the stuff I'm going to be talking about today. And so this is the plot on the top right here, this feature importance vector. So it's effectively a probability vector that we learn over all of our input features that weights the relative importance of their contribution to the clustering error. So when we have a set of clusters, we also have a matrix of probabilities that assigns each data instance to each one of the clusters. That's the bottom left-hand plot there. And then also simultaneously, we also learn a set of conditional probabilities, which is how we predict the phase. So if you're in a given cluster, we have a prediction of the class with kind of some set of probabilities that, again, those are specific to each cluster. And so that's all you really need to know to hopefully be able to understand what I'm going to be talking about for the rest of the talk. If there are questions, though, I do have the kind of the mathematical details at the end of the talk. Okay, so what we're using as the data here Basically, we take, again, just data that comes from the kind of satellite era, so post-1980 onwards. In this case, we take sea surface temperatures globally, or almost globally, within plus or minus 60 degrees in latitude. We take, in a kind of equatorial slice in the Pacific Ocean, we take the vertical derivative of temperature as a kind of proxy for thermocline variability. And then also in a box centered on the tropical Pacific, we take the surface wind stresses. And so these come from Era 5. The sea surface temperatures also come from Era 5, or the boundary conditions from Era 5, which really means it's had SST and then a kind of more recent period satellite observations. And then the subsurface data comes from the Aura S5 reanalysis, also by ECMWF. And so what we do is we take that data and we perform a delay embedding. So we stacked lagged instances of the data in time. Here we use a 12-month embedding window. So we try to take a full year's worth of data, stack it all together, and then we do an EOF analysis on that. And so then what we get from that is a set of spatiotemporal patterns, or the EOFs, for each mode of the decomposition in both SST, DTDZ, and wind stress. What we use as the features then is just the principal components, but we keep a fairly large number of each of these. So we keep roughly 150 of these for the sea surface temperature, 130 for the DTDZ modes, and then on the order of 100 for the wind stress field. With the idea that our learned feature importance can help distinguish which one of these are actually important for the classification task, and kind of zero out the ones that are uninformative for the particular task of classifying the ENSO phase. So yeah, again, quite briefly going through this, we formulate the problem as trying to predict the phase of ENSO as one of three classes based on thresholding El Nino 3.4 index. So if it's above 0.5 degrees, it's considered El Nino. In between that is neutral, and below minus 0.5 degrees is La Nina. And then for a given start date in our evaluation period, which goes from January 2002 to December 22, we produce a series of forecasts from 1 month lead time all the way up to 24 months in 1 month increments, with an ensemble of 50 separate ESPAR models. So I also want to note here that each model basically just produces one forecast in at a given lead time, and then each forecast is kind of completely independent, and each month of each forecast is also completely independent. So it's not like we're just training one model. We actually retrain a given model for every single forecast and then repeat that as we go through our evaluation period. And you might ask why you do that. It's basically because we can afford to do it, because training one of these models is very, very cheap, on the order of a second or something like this, just on a single node. So that's kind of due to the formulation of the algorithm itself. So basically, we have a very large number of models that we're training throughout this evaluation period, something like 300,000. And so kind of this then motivates the need to try and do some kind of reduction of that large ensemble if you're actually trying to interpret it. So just a few more details on how we actually do the ensemble forecast. So for a given year and a given month in our evaluation period, we only use data that's available up to the kind of month that we're making the forecast from. So we don't include any data from the future. We basically they also restrict the number of instances to just be those that are relative, plus or minus 1 month, to the target month that we're trying to predict from. This helps enforce kind of seasonality in the precursors. And so yeah, we basically, what the schematic on the right is showing is that we train our full ensemble of models. We kind of aggregate their predictions to get one single prediction for the ensemble, and then we proceed and do the same thing for the next month. But we also provide the predictions from the previous month as input features to our following month's forecast, as a way of kind of conditioning on what the previous members in that forecast have already done, and this kind of helps chain the forecast together as you go out in lead time. Crucially, in this analysis that follows, we only keep models from that ensemble whose predictions are kind of verified to be correct. So here we're not worrying about a skill assessment at all. We throw away all the incorrect models and just keep the correct ones and try and interpret why their predictions are actually correct. Okay, so now for some of the results. So these plots here are showing that feature importance vector, where on the x-axis here we have our index. So this is our kind of principal component mode. The first 1 to 152, these are our SST modes. Then the next 130 or so, these are the T to Z, and then after that's the wind stress. And then the few on the end, those come from the probabilities from the previous month's forecast. So we're going to ignore those. Basically what you can see here, so this is ordered by lead time, so we go from 3 months all the way out to 24 months. You can see at the kind of shorter month lead times, we really only need to know the first handful of leading modes as ordered by variance in each of the fields to be able to make the prediction correctly. But as you go out longer and longer lead times, you need to pull in information from more and more PCs in each of the fields, which kind of basically corresponds to our precursors are becoming more diverse as we go out in lead time. We need to know information coming from the extra topics rather than just the tropics as well. Perhaps more interesting is rather than just look at a weight on each PC, we can recombine these with the EOFs and visualize that importance as a kind of spatial map, or here a spatial map, but I'm showing every single lead time in a kind of descending order. How we do this is we basically take a weight times the eigenvalue times the EOF, square it, and then sum all of that. And then, so that gives you a kind of kind of spatial intensity, if you like, of where the kind of how the difference in feature weights corresponds to different regions of being deemed more important. Here I've also sorted it by 2 specific target seasons, so July, August, September on the left here, November, December, January on the right here. Just to show some interesting differences when you're looking at different target seasons, where the models end up looking at kind of different regions of our kind of 3 input fields, with different weights. So you can see in the July, August, September, for example, more weight being placed on the tropical Pacific relative to in November, December, January. Some other kind of interesting things that strike out, you'll see this in a moment on the right-hand slide. In NDJ, you get a much greater weight being put on the tropical Atlantic, whereas you don't really see that at all in the corresponding July, August, September forecasts. We can also, I'm going to speed up. This is going to be quite helpful if you do end up looking at the web results. So we can also kind of aggregate all of the individual model clusters into what I'm calling superclusters. So each of our individual ESPAR models fits a set of clusters to our weighted feature space. So that's what these blue crosses are showing here. We can kind of aggregate all of those. So yeah, we should say each of these corresponds to a particular pattern, basically. So it's a point in a latent space. We can decode it using the EOFs and get a spatiotemporal composite. We can, rather than do this for every single model of all 300,000, what we do is we fit a new model just to those cluster centroids to get a kind of aggregated cluster or a supercluster. It's this cross in black here, and then we just visualize that. And so this kind of dramatically reduces the number of composites that we have to visualize and makes it kind of tractable to actually look through all this stuff in person. And so, again, just quickly, what you get is stuff like this. So for different points in our phase space, we get different spatiotemporal composites, again, in those same 3 fields. How long do I have? Yeah, I'll skip through this stuff. Probably, the interesting thing you can do then is for particular target months in our evaluation period, we can look at the spatiotemporal composites or the reconstruction based on all of those different spatiotemporal composites from our model predictions, that's on the far left, versus the observations in the middle. And on the right here is this kind of measure of what's called structural similarity, which you can think of basically as like a local pattern correlation between the 2 fields, as kind of another way of showing where does the model reconstructed field agree best with the observations on that same date prior to the target date. Again, as a way of kind of highlighting presumably where the agreement is best is also the regions that were most important to know in the precursor to that particular forecast that we were making for that date. And so that's about all I have time to talk about. So there's many different things you can do to extend this One thing I will say is that you could easily repeat this on climate model output as a way of kind of helping potentially diagnose issues with ENSO predictability in that particular model. And I'll leave it there, I think. Thank you very much.